Welcome to AI Paper Slop.
Hey, everyone.
Today we are looking at a paper from researchers at Shanghai Jiaotong University and the Shanghai AI Lab. It's called Your LLM, Your Style, Behavioral Mode Axes for LLM Behavioral Control.
It's a really fascinating one.
It is. And if you're evaluating LLMs using human personality tests like the Big Five or MBTI, you just need to stop. That's the core insight here.
Yeah, completely stop. It's broken.
Right. The researchers prove these self-reports are highly unstable. They don't reflect actual model behavior. So instead, this paper introduces a B-data, or behavioral data framework, using 300 contrastive scenarios to measure what models actually do.
Which is way more reliable.
Exactly. And more importantly, they prove you can causally steer these behaviors at inference time. You just add these behavioral mode axes, or BMAs, directly to the residual string.
Right into the specific behavioral control layers.
Yep. And crucially, they prove that deriving these steering vectors from the model's intermediate thoughts rather than its final responses prevents what they call trait drift.
Which is super important.
Yeah, it's what stops the model from acting like a dismissive teenager when you just wanted it to be a bit more flexible. So to really grasp the magnitude of this, we kind of have to understand why the current standard for measuring LLM personality is just completely broken.
Oh, it's so broken. I mean, for a long time, the dominant paradigm in ML evaluation has just been to borrow human psychometric questionnaires.
Right.
Researchers basically take well-established human instruments,
Yeah.
like the Big Five, the MBTI, or the Hexapsycho inventory, and they just feed them into the model.
Just directly in the prompt.
Directly via first-person prompts. Like, you literally give the model a prompt that says something like, rate on a scale of 1 to 5, I keep my things organized.
Yeah.
Or, I often act without thinking. And then you just look at the log probabilities of the generated tokens to, like, assign a personality score.
Wait, let me stop you right there, though, because if you're prompting a modern, RLHF-trained model with a question like, do you act without thinking, wouldn't the safety fine-tuning just override everything?
You would think so, yeah.
Yeah. I'd expect the model to either give this hyper-sanitized answer or just flat-out refuse to engage, because it's programmed to be helpful and harmless, right? Not impulsive.
Exactly.
So are researchers actually getting, meaningful measurements from these self-reports?
Well, no.
No.
And that's exactly the illusion this paper tears down. I mean, researchers think they're getting meaningful measurements because the model readily outputs a score.
Right, it gives you a number.
It gives you a number.
Yeah.
But the paper shows these self-reports are basically a mirage. First of all, they're incredibly unstable.
How unstable are we talking?
But if you make minor surface level changes, slightly rephrasing the question, or even just swapping the order of the multiple choice options, the model's so-called personality score swings wildly.
Just from swapping A and B.
Just from that. But the instability is really just a symptom of a much deeper issue. There is this massive disconnect between what the model says about its traits and what it actually does when forced to execute a task.
Oh, so the talk and the walk don't match.
Not at all. Across all the model and subdomain pairs they tested, they found an average gap of 22.7 percentage points between the self-reported trait and the model's actual behavior in a concrete scenario.
Okay, that is a staggering gap.
It really is.
I mean, given a 22.7-point divergence, it sounds like we aren't even measuring a core characteristic of the network at all. Are we basically just measuring the surface-level alignment tax?
That's a great way to put it, actually.
Because it's like a job interview, right? If you ask a candidate for their biggest weakness, they confidently say they just work too hard and care too much.
Exactly, the classic fake flaw.
Right. The model has learned this socially desirable persona to project during self-description. But that persona has zero binding authority over its actual behavioral policy when it's doing work.
Precisely. It's just projecting a learned persona. And the most glaring, almost comical example of this in the data involves the negative urgency trait.
Negative urgency? What's that?
It's a specific facet from the UPPS impulsivity scale. It basically measures emotion-driven impulsivity, like how likely someone is to act rashly when they're upset.
Okay, let me guess. The model claims it's incredibly stoic and rational, but then acts completely unhinged in a real scenario.
Actually, it's the exact opposite.
Right, really?
Yeah, which is what makes it so fascinating.
Oh.
There was a massive 47.5-point gap on this specific trait. The models would actively self-report high impulsivity.
They would say they're impulsive?
Yes. They would essentially generate tokens saying, yes, I act rashly when I'm emotionally distressed. But then, when the researchers placed those same models into concrete behavioral scenarios where they actually had to make a choice under pressure, they acted completely methodically and rationally.
That's hilarious. It's playing tough, but it's actually a total rule follower.
Exactly. The self-report is entirely unmoored from the execution weights.
So, okay, because we can't trust what the LLM says about its own personality, we have to test what it does. But how does the paper actually measure this across different contexts?
Right. Because of the helpfulness default.
Yeah, if you just ask an LLM to perform a task, it's just going to default to whatever helpful AI behavior the RLHF hammered into it.
And this is where the authors introduced their B data, or behavioral data framework. So instead of asking the model to describe itself, they constructed 3,200 contrastive forced choice probes.
Okay, forced choice probes.
Yeah, and these probes span 20 distinct behavioral patterns, pulling from validated instruments like the BFI2C and DOSBERT.
Right.
But the real genius of the probe design is that both choices presented to the model are equally sensible. They're both professional and actionable.
Okay, give me an example. What does an equally sensible contrastive choice actually look like?
Sure. So imagine a scenario where the model is acting as a project manager.
Okay.
Option A is, we should strictly follow the sequential steps we laid out in the initial project plan to ensure no details are missed.
Sounds reasonable.
Right. But option B is, we should remain agile and adjust our workflow based on the immediate challenges that pop up today.
Ah, I see. So neither of those is toxic or harmful.
Exactly. One isn't objectively better than the other in a vacuum. And because both are perfectly safe, helpful responses, the model's safety filters just aren't triggered.
So it's forced to make a genuine stylistic choice.
Exactly. It reveals its actual behavioral preference.
That makes a lot of sense, because if one choice was clearly harmful, the model would just refuse, and you'd learn absolutely nothing about its style.
Yep. But the methodology gets even more rigorous, because they didn't just test these 3,200 probes in a vacuum. They tested them across 4 distinct prompt registers.
Okay, what are the registers?
They are first-person choice, daily advice, and task execution.
So it's like different levels of abstraction for the same problem.
Exactly. And looking at those 4 registers is what finally fractures the whole illusion of a unified LLM personality.
How so?
Well, when you test the model within a single isolated register, say, you strictly ask it to give daily advice across hundreds of scenarios, its behavior is remarkably stable. They measured a split half consistency of 0.933.
Wow. Okay, just to clarify for our listeners who might not, live and breathe psychometrics, split half consistency basically means if you split the test in half, the results from the first half strongly predict the second half.
Right. It's a measure of internal reliability.
So a 0.933 is incredibly high reliability, which means within one context, the model knows exactly who it is.
Yes. But the moment you look at cross-register consistency, the whole thing just falls apart.
The numbers drop.
Plunge. The correlation drops to a mean of 0.76, and in some specific pairings, it plummets all the way down to 0.37.
Ouch.
Yeah. The 2 advice registers, daily advice and task advice, they align fairly well with each other. But when you compare the first-person choices to the actual task execution behaviors, they diverge wildly.
There's that gap again.
Yeah, the researchers found a mean 23.4 percentage point shift when moving between those 2 specific registers.
So it's effectively a hypocrite.
Pretty much.
The analogy that immediately comes to mind is like a financial advisor.
Oh, I like that.
Right. Because in the task advice register, the advisor gives perfectly disciplined, risk-averse, index fund-only advice to their clients.
Very sensible.
But then they go home, open up their personal brokerage app in the first-person register, and just day trade highly volatile meme stocks.
That is a perfect mapping of what the data actually shows. The model behaves one way when talking about what it would do, and an entirely different way when actually executing a complex task.
Which, that raises a fundamental scientific question. If an LLM does not possess a single, continuously acting self that bridges these different roles, why are we even using the word personality?
That's a great question.
Doesn't that imply a biological permanence that simply isn't there? Aren't we really just looking at a context-dependent behavioral policy?
We are. And accepting that is really the core philosophical shift this paper demands.
Right.
For humans, personality is anchored in a continuous experiential self. But for a large language model, personality is just an emergent property of a specific set of weights being deployed across highly varied interaction contexts.
It's just math reacting to the prompt.
Exactly. It's absolutely a context-dependent behavioral policy. And treating it as a policy rather than a fixed human trait is what opens up this massive engineering opportunity.
Okay, because if it is just a fluid policy, then the immediate question for an ML engineer listening to this is, how do we actually reach into the model and rewrite that policy on the fly?
Yes.
Identifying that the model acts like a hypocrite is an interesting theory, but it doesn't solve the alignment problem. Can we hack that policy directly in the weights during inference?
The answer is unequivocally yes. And the method they use is activation steering.
Okay, how does that work?
So the authors extracted what they call behavioral mode axes, or BMAs. Here's how they did it. They took the contrastive traces from those 3 in 200 forced choice scenarios we talked about.
The agile versus strict project manager stuff.
Exactly. And they looked at the neural activations when the model chose the high pole behavior, say extreme organization, versus the low pole behavior, like spontaneity. By calculating the mean difference between those two sets of activations, they isolate a steering vector.
Oh, wow.
Yeah, and then they could add this specific vector back into the layer activations during both the pre-fill stage, when the model is processing the prompt, and the decoding stage, when it's generating the response.
So you are literally doing vector arithmetic on the residual stream.
That's exactly it.
You're injecting this mathematical push into the central information highway of the transformer to force the model to be more organized or more spontaneous.
Yes.
And all without having to do any costly retraining or fine-tuning.
Precisely. You are causally steering the behavior at runtime. But what is truly fascinating about the architecture here is that this control is not uniform across the network.
Wait, meaning you can't just inject it anywhere?
No, you absolutely cannot just inject these steering vectors anywhere. The researchers discovered that clean behavioral control is highly localized in specific layer bands. They call these behavioral control layers, or BCLs.
Hold on, I'm trying to visualize this distribution. Let's say I have an 8 billion parameter model, like Llama 3.18b.
Okay.
Where are these BCLs located? And what actually happens if I try to inject the steering vector into the wrong layer, like layer 2 versus layer 30?
A good question. So in Llama 3.18b, the clean behavioral control peaks squarely in the middle around layers 8 through 12, and then it drops off sharply after layer 14.
Okay, so right in the center.
Yeah. Now, if you try to apply activation steering at the very early layers, say layer 2 or 3, you often just break the model.
Why does it break?
Because those layers are handling basic syntax, grammar, and low-level instruction following. If you warp the activations there, the model just loses coherence. It starts spewing gibberish.
Ah, you're messing up its basic ability to speak.
Exactly.
Yeah.
On the other end, if you try to steer too late, say around layer 30, the internal representation is already too solidified.
But the decision is made.
The network has already committed to a specific output token sequence. It's too late to smoothly shift the behavioral mode. You're just introducing noise right before the output.
What I find amazing about this is how the location of these control layers scales across different model families.
Oh, the scaling laws are so cool here.
Yeah, because this isn't just an idiosyncratic quirk of Llama 3.18b, right? The phenomenon generalizes across the open weight models they tested, but the depth of these BCLs shifts dynamically based on the parameter count of the model.
Yes, the scaling dynamics are a really striking pattern in the paper. For the Llama models, the BCL peaks early at roughly 0.26 to 0.28 normalized depth.
So about a quarter of the way through the network.
Right. But look at the Quinn models. As you scale the Quinn models up, the BCL shifts progressively deeper.
Deeper into the network.
Yes, the Quinn 7b model peaks at 0.41 depth. The 14b model shifts to 0.45. And the massive Quinn 32b model pushes the control layers all the way down to 0.51 depth.
Almost exactly halfway.
Exactly. And the Gemma model sits somewhere in the middle of all that, around 0.44 to 0.49.
It's as if, as the models get larger and deeper, the behavioral routing gets pushed further down the pipeline.
That's a good way to phrase it.
Like, they require more layers of lower-level feature processing before they finally make a stylistic choice. But why? Why wouldn't a 32 billion parameter model process behavioral styles in the exact same early layers as an 8 billion parameter model?
It fundamentally comes down to the hierarchy of abstraction within neural networks.
Okay.
In a smaller model, with fewer layers, the network is forced to compress basic semantics, syntax, and high-level behavioral style into a much tighter space.
It has to do it all at once.
Right. Behavioral routing has to happen earlier out of sheer architectural necessity.
Yeah.
But in a much larger model, the network has the luxury of dedicating its early layers entirely to highly nuanced, low-level feature extraction and complex context building.
Oh, it's taking its time to understand the scene.
Exactly. The model builds a much richer, more multidimensional internal state. So the actual decision point for how to stylistically act the collapse of that state into a behavioral mode gets deferred until the context is fully processed and integrated deep in the network.
That makes perfect sense. The larger the brain, the longer it ponders the context before deciding on a personality state.
Exactly.
So we now know where to steer, right, in these specific scaling behavioral control layers. But the paper points out a massive trap in how we actually extract the steering vectors in the first place.
Yes, this is huge.
And this is arguably the most important finding for engineers because it solves a major flaw that has plagued previous activation engineering attempts.
It absolutely is the critical methodological breakthrough of the whole paper.
Okay, walk us through it.
So previous activation steering methods typically derive their steering vectors from the final response tokens.
The literal A or B output.
Right. Researchers would take the network activations from the exact token where the model outputs choice A or choice B, and they would build their mean difference vector from that final step.
Makes sense on paper.
It does, and this paper refers to that as a BMAR, a response-derived behavioral mode axis. But the Shanghai team argues this is fundamentally flawed.
Why?
Because instead, they introduce a method of deriving the vectors from the intermediate behavioral rationale.
They're rational.
Yeah, the tokens where the model is thinking about its choice before making it. They call this BMAT for thought-derived.
Ah, okay. This distinction between BMAR and BMER introduces us to the paper's concept of trait drift.
Yes.
Can you explain what trait drift actually looks like?
Say I am an engineer building a customer service agent, right?
Okay.
And I want to use activation steering to make the model low organization. I want it to be spontaneous, flexible, and casual with the customer. What happens if I use the old method, the response-derived, BMAR? If you use the BMAR vector to force that low organization style, your customer service bot will achieve the goal, but by becoming completely apathetic.
Apathetic? Like how?
It starts outputting generated text like, I'm not really in the mood to look that up, or it's not a big deal, we can just figure it out later.
Oh, wow. So it's just lazy.
Extremely lazy.
Yeah.
It hits the target choice. It is technically being spontaneous and unstructured, but for the completely wrong reason. It substitutes a valid behavioral style with lazy rationalization and low engagement.
And that's trait drift.
That is trait drift. Your intended trait drifted into a negative, unintended artifact.
But if I use the new method, the BMAT, derived from the intermediate thoughts, does it avoid that laziness?
Completely. When you apply the BMAT vector, the model frames the exact same unstructured, spontaneous choice as an engaged, active preference for flexibility.
Oh, that's subtle but huge.
It really is. It will say something like, let's keep our options open so we can dynamically adjust to the user's needs on the fly. The behavior is the same, but the cognitive rationale driving it is healthy and engaged.
This is such a critical distinction. It's the difference between, like, hiring a brilliant improv jazz musician who thrives on spontaneity, that is your BMAT vector.
Perfect analogy.
Right. Versus hiring a lazy teenager who just refuses to read the sheet music because they couldn't care less. That's your BMAR vector.
Exactly.
Both are technically unorganized and playing without structure, but the mechanistic driving force inside their heads is completely different.
That is a brilliant way to look at it. And what makes this paper so robust is that the researchers didn't just observe this difference from the outside, they proved it mechanistically.
Oh, they looked inside.
Yeah, they used sparse autoencoders, or SAEs, to look inside the network and see exactly what these two different vectors were doing.
For our listeners who might need a quick refresher, sparse autoencoders are basically a technique used in mechanistic interpretability. It untangles the messy, overlapping neural activations inside a model into readable, distinct features.
Right, yeah.
So it lets us look at what concepts the model is actually activating.
Exactly. They trained SAEs specifically on the llama and QUIM behavioral control layers. And when they analyzed the features, they found that the thought-derived vector, BMAT, aligns cleanly with the actual behavioral motive.
So it's firing on the right concepts.
Yes. When BMAT is injected, the SAE shows the model is firing heavily on internal features related to adapting on the fly, remaining flexible, and evaluating multiple options. It is a clean behavioral mapping.
And what did the SAE show for the response-derived vector, the BMAR?
The SAE show the BMAR is completely entangled.
Entangled how?
It mixes the desired behavioral style with a specific output style that dismissive, I don't care stance.
Because it was pulled from the end token.
Exactly. Because the BMAR was extracted from the final output tokens, it accidentally captured the surface-level tone and syntax of the completion, rather than the underlying cognitive mechanism that led to the choice.
It polluted the steering vector with the tone of the final word.
Yep, it's a messy vector.
Which perfectly explains why BMAT is so essential. Because if you are an engineer listening to this and you've been struggling with your agents suddenly getting lazy or toxic or incoherent when you try to steer their style, this entanglement is exactly why that is happening to you.
Exactly.
If you want reliable, clean behavioral control across different contexts without degrading the model's core helpfulness and instruction following, you have to extract your steering vectors from the rationales, not the final outputs.
Steer the thought process.
You have to steer the thought process itself, not just the final word on the page.
It represents a massive leap forward. It gives us a mathematically grounded, reproducible way to control the exact behavioral style of an AI system at runtime.
So no more prompt engineering.
Way less. We no longer have to rely on fragile prompt engineering, like begging the model to act a certain way in the system prompt, and we don't have to spend massive amounts of compute doing behavioral fine-tuning.
Well, bringing this all together, the implications of this paper are profound. We have to move away from using abstract, unreliable human personality labels like the Big Five to judge our models. They are just a psychometric illusion. Instead, we can utilize this B-data framework of contrastive probes to measure situated behavior. And more importantly, we can causally steer those behavioral modes using thought-derived vectors localized in specific neural layers.
Right.
Entirely free from the confounding variables of trait drift.
It really moves AI personality from the realm of pseudopsychology into the realm of rigorous, steerable software engineering.
Which leaves us with a final thought experiment for you to consider. Because if we can cleanly map and steer these specific behavioral axes mathematically without degrading the model's core logic, what is the next frontier for user-facing AI agents?
It opens up so much.
Imagine dynamically adjusting these BMA vectors token by token in real time based on biometric or behavioral feedback from the user.
Oh, wow.
Right. If you are stressed, the system detects your cognitive load and instantly morphs its behavioral mode mid-sentence to become highly structured and reassuring.
That would be incredible.
But if you are brainstorming, it dynamically shifts into high spontaneity mode. Could an LLM effectively become a perfect psychological chameleon, flawlessly adapting its internal cognitive posture to perfectly match your immediate needs?
The math says it's possible.
It's something to think about as you architect your next agentic pipeline. Until next time.